Lighthouse Scientific Education presents a lecture in the Solutions and Water series. The topic? Solutions and Solubility. The lecture is designed so that the student can pick and choose to view specific subtopics of the lecture. As with many of our lectures, not all students will need to be exposed to all the material covered. Be aware what is expected of you. Material in this lecture relies on an understanding of the previous lectures, fundamental properties of matter, ionic bonding, and intermolecular forces. The first part of the lecture starts with some basic definitions and categories of solutions. There are quite a few of them. Then, a look at solution formation, with a specific focus on forces and energy. The second part of the lecture deals with solubility and is limited to solubility with liquid solvents. Factors affecting solubility will be explored, as will the solubility of solids and liquids. The solubility rules of ionic compounds in water are reviewed. The final topic is the solubility of gases. Henry's law will be introduced. First to the definitions. Some of these definitions we've come across before, but some are new. A term we've seen before is solution. It is a homogeneous mixture of two or more pure substances. Within the solution is the solute. It is a substance that is dissolved in another substance. The other important component of the solution is the solvent. It is the substance that dissolves the solute. Together, the solute and the solvent are a solution. Perhaps the most familiar solution begins with the solute of salt, sodium chloride. Equally familiar is the solvent H2O, water. Adding salt to water, with perhaps a bit of stirring, creates the solution salt water. Solution is often abbreviated SOLN. The salt is dissolved or dissociated in the water, and together they form a solution. Is there a limit to how much salt can be dissolved in a set volume of water? Yes, there is, and that limit is referred to as the solubility of the salt in water. Specifically, solubility is defined as the ability of a substance, solute, to dissolve in a solvent. A solute capable of being dissolved in a solvent is said to be soluble. Some solutes are not soluble in a solvent, and they are said to be insoluble. Sodium chloride is soluble in water, but only to a point. That point is called its saturation. A saturated solution contains as much solute as the solvent can dissolve. The concentration is at the saturation point. Additional solute will not homogeneously mix in the solvent. If our cartoon salt water solution represents a saturated solution, then the addition of any more sodium chloride will only result in the additional solute sinking to the bottom of the vessel. The solute would be referred to as being a precipitant or having precipitated. A precipitation, abbreviated PPT, has the solute in a different phase from the solution. Rain is considered a precipitation because it is in the liquid form of water as opposed to the vapor phase in the cloud. Returning to the saltwater solution, if the amount of solute is less than that of the saturation point, the solution is considered an unsaturated solution. By definition, that means the solution contains less than the maximum amount of solute that the solvent is capable of dissolving. Slightly outside of the saturated-unsaturated definition sits supersaturated. That is when more solute is dissolved in solution than normally allowed. It is condition dependent and unstable. It is also a topic that doesn't get much play at this level of chemistry, and we will not mention it again. Sometimes there is confusion with the term solution. Often students think that a solution has to be a liquid, but that's not the case. Referring back to the definition of solution, it is a homogeneous mixture of two or more pure substances. Nowhere in there does it specify the states of matter. A solution can actually be a gas, liquid or solid. A table that catalogs solution, solute, and solvent by state of matter should highlight the diversity of the term solution. Starting with the solution that is a gas. For a solution to be a gas, both the solvent and the solute have to be gases. An example is air. Nitrogen is the most abundant form of gas in our atmosphere and can be considered the solvent. A less abundant form of gas is oxygen, which is called a solute. There are additional solutes in the solution we call air. For solutions that are liquid, there is a liquid solvent and liquid solute. Rubbing alcohol is a good example of this type of solution. It contains both water and isopropyl alcohol. The alcohol is usually in greater quantity and is considered the solvent. An important term associated with this type of solution is miscible. It implies that the liquids involved in the solution, the solvent and the solute, will mix completely together in all or nearly all proportions. Contrast that with immiscible. These are liquids that do not mix completely and generally form separate layers. Oil and water is a good example of immiscible liquids. Think of how salad dressing will separate into different layers when left to sit. There are other types of solutions that are liquids, including those that are composed of liquid solvent and a gas solute. Carbonated water or soda is a good example. Yes, some of the gas, as bubbles, does leave this type of solution, but there's always gas remaining dissolved in the solvent. The third type of liquid solution has a liquid solvent and a solid solute. The saltwater example used earlier serves well here. The final two types of solutions are solids. This is where the common use of the term solution as a liquid comes in conflict with its use in chemistry. There are solid solutions that are composed of solid solvent and solid solute. Metallic compounds such as brass or steel are this kind of solution. Steel can also be categorized as a compound, so there can be overlap in definitions. These solutions are also referred to as alloys. The definition of an alloy is a substance composed of two or more metals, or a metal and a nonmetal. The last solution in the table is a solid that has a solvent that is a solid and the solute that is liquid. These solutions are not as common as the other solutions. An example is a dental amalgam that is used to fill cavities in teeth. While this is a busy table, the solutions that get the most attention in this lecture are the liquid solutions with solutes as gases or solids. We will be returning to these solutions after finishing up with a few more definitions. These definitions represent a broadening of the previous definition that has a solution as a homogeneous mixture of two or more pure substances. There are two important kinds of solutions that are not homogeneous mixtures that fall under the heading heterogeneous solutions. The first one is a suspension, that is a fluid containing solid particles that will eventually settle out. Consider this cartoon representation of the solution that has particles, colored as yellow dots, that are distributed throughout the solution. After some period of time, if undisturbed, the particles will settle or sink to the bottom of the solution. The particles are not considered dissolved in the solution, but rather mixed in. Common suspensions include sand in water and dust in the air. Given sufficient time, both types of particles will settle out of the solution. Yes, they can be redistributed in the solution with some agitation. The other type of heterogeneous solution is called a colloid. This is a solution with small particles of varying size on the order of 1 to 100 nanometers that are evenly distributed throughout. A murky appearance is often associated with colloids. Because the particle size is so small, it is very difficult to filter them out. Also, because of the small size, the particles tend to stay suspended in solution. This cartoon representation has particles with a distribution of sizes. Commonly found colloids include fog, water droplets of different size, liquid, evenly distributed within the air, a gas solvent. Smoke, tiny particles of ash, solid, distributed in the air. Emulsions, that is where small particles of one liquid are evenly distributed within another. Milk and mayonnaise can be considered emulsions since it has small drops of fat distributed within a water base. Same goes for cheeses and jellies. That concludes the definition portion of the lecture. Solution formation can be approached from a mechanical perspective using the lens of energetics. Favorable energetics has solutes dissolving in a solvent. Unfavorable energetics describes an insoluble solute. The energetics of a solution formation can be broken down into three parts. These parts are not a description of the actual formation of the solution, but rather a way to consider the costs and returns of creating a solution. It goes like this. The first part is the cost or energy of separating some of the pure solvent particles from each other, breaking intermolecular bonds. Cartoon example has a beaker of solvent in the liquid form. Liquid is used for convenience and depicted as spherical particles. Particles in the liquid are attracted to each other, intermolecular bonding, but can still move freely past each other. It will be necessary to break some of these interactions so that the solute particles can interact with the solvent. The volume's been increased in anticipation of the solute particles. Breaking intermolecular interactions costs energy. In the same vein, there is the energy cost of separating solute particles. Solute particles can also be thought of as initially existing in a beaker with some sort of intermolecular interactions occurring between the particles. When they are in a solution, some of those intermolecular interactions will need to be broken so that new solvent-solute interactions can be formed. Energetically, breaking intermolecular bonds costs energy. If this were the only two steps, then there would never be solution formation because the process would only involve steps that cost energy. But sometimes there is solution formation, so a third step is needed, and that is for solute and solvent particles to interact. These interactions release energy. Not always a lot, but matter interacts with matter. With these three energy terms, the overall energetics of solution formation can be examined. There are two scenarios. If the magnitude of the combined costs of step 1 and 2 is less than the magnitude of the energy released in step 3, the solute is soluble in the solvent. Solution formation is favorable. If, however, costs of step 1 and 2 is greater than the energy released in step 3, then the solute is not soluble or insoluble in the solvent. It just costs too much for what is gotten by mixing. This concludes the solution parts of the lecture. It is also the starting spot for the second major part of the lecture, solubility. Breaking down the process of solution formation by energetic steps is useful in evaluating factors affecting solubility. In this lecture, we will limit the discussion to solvents that are liquids. As mentioned earlier, solubility is the ability of a substance, a solute, to dissolve in a solvent. Another way of saying that is that the solute is capable of being dissolved. A substance is defined as soluble if more than 0.1 grams of it will dissolve in 100 mils of solvent. Solubility and factors affecting solubility can be viewed from several perspectives. Listed here is an overview of factors or perspectives that are covered in the solubility part of the lecture. We will spend some time with each one. One aspect of solubility is the speed of dissolving of the solute. There are factors related to the properties of the solute and solvent, and there are mechanical ways of speeding up the process. And then there is the most useful phrase in solubility, like dissolves like. The phrase reduces favorable solute-solvent interactions to polar-polar or nonpolar-nonpolar. Temperature also plays a role. The temperature dependence of solubility for liquid and solutes is generally opposite of that for gases. Each will be addressed in its own section. Pressure dependence also varies between the liquid and solid solutes and the gas solute. First are the factors that affect the speed of dissolving. It should be noted that these factors are generalizations and are not absolutes. The biggest driver in the speed of dissolving is the amount of surface area of the solute. Since the favorable formation of a solution is a function of the solute-solvent interactions, it should not be too surprising that the more accessible surface area of the solute will mean more solute-solvent interactions. The more solvent molecules that can intermolecular bond with a solute particle, the greater the release of energy. This often translates into faster dissolving. With that in mind, it is not uncommon for a solute to be crushed as a way to increase surface area and speed the process along. Another helpful technique is stirring. It uses the same argument in that it produces more solute-solvent interactions, which is synonymous with faster dissolving. Bottom line, the more contact the solute has with the solvent, the faster it dissolves. The next concept with solubility is perhaps the most famous statement in chemistry. It is like dissolves like. And by like or dislike, the criteria is between polar and nonpolar, Apolar is also a term used for nonpolar. Specifically, polar solvents readily dissolve polar solutes. Polar solvents like polar solutes. And nonpolar solvents dissolve nonpolar solutes. Nonpolar solvents like nonpolar solutes. By extension, nonpolar substances do not like or dissolve in polar substances. This phrase is faster and easier to use than an analysis using the 3 energetic steps as listed above. Still, within the refrain like dissolves likes are the 2 cost steps and the 1 energy releasing step. For example, a nonpolar solute should not dissolve in a polar solvent. They are not likes. Energetically, the cost of separating the particles of the polar solvent and the cost of separating the nonpolar solute particles is not sufficiently paid for with the release of energy of the polar-nonpolar intermolecular interaction of the solution. The insolubility of the nonpolar solute in the polar solvent is the result of costs exceeding returns. What about solute molecules that have both polar and nonpolar characteristics? These molecules are not as easy to categorize as soluble or insoluble in a particular solvent. They contain both like and dislike qualities. A look at how well different organic alcohols dissolve in water will show that the ratio of polar to nonpolar character determines the level of solubility. Consider the smallest organic alcohol, methanol, CH3OH. It has a nonpolar methyl group, CH3, and a polar hydroxyl group, OH. The hydroxyl group is the alcohol. Organic alcohols will dissolve or mix into the polar solvent water to the degree to which the polar component, the hydroxyl group, is of sufficient proportion as compared to the nonpolar component, as measured here by the amount of carbon-hydrogen bonds. In the case for methanol, the hydroxyl group comprises a sufficient proportion of the molecule so that it completely dissolves in the polar solvent. It will do so at all concentrations. It is infinitely soluble. The 2 liquids are said to be miscible. But what happens with alcohols that have larger nonpolar components? This can be shown by increasing the number of carbons and hydrogens in the alcohol while keeping the polar characteristic constant, a single hydroxyl group. It should be noted that C2H5OH is ethanol, which is the compound commonly referred to as alcohol, and is a substance found in beer and wine. Descending the table has the alcohols acquiring proportionally more nonpolar character. Back to the ethanol. It has enough polar characteristic to completely dissolve in water in all proportions. Same thing with the propanol, C3H7OH. It is not until butanol, C4H9OH, that we come across an alcohol with sufficient nonpolar characteristic to limit the solubility of the alcohol in water. Here, the solubility of butanol is 8.0 grams per 100 ml of water at 25 degrees Celsius. It is not completely miscible in water, but makes the cut as soluble. The larger nonpolar characteristic of the alcohol, 4 carbons bonded to 9 hydrogens, limits its solubility. Also note that a solubility value has to be given at a particular temperature. More on this later. Returning to the table, having even more carbons further limits the solubility. At some point, the alcohol is no longer considered alike with water. The take-home trend is that the more carbon hydrogens a substance has, the more nonpolar it is, and the less soluble it is in water. The next solubility trend, under the likes dissolve likes banner, is salt or ionic compounds in water. It is a topic that was originally discussed in the ionic bonding lecture and further developed in the intermolecular forces lecture. When dealing with the solubility of an ion in water, the term dissociation is used. Dissociation is more than just dissolving. For ionic compounds, dissociation is dissolving in a solvent into its constituent ions. The term dissolving can still be used with ionic compounds, but it implies dissociation. Solubility is the degree to which the compound dissociates. Another way to think of the solubility of an ionic compound is that the more soluble a compound is, the larger the concentration of dissociated ions is at the saturation point. More soluble means more dissociation. The example used in the previous lecture was the salt sodium chloride dissolving or dissociating into solvated ions. As said, polar solvents dissolve polar solutes. Remember that polar bonds have partial charges. Polar-polar interactions are electrostatic interactions of the partial charge. It is not too big of a leap to extend the electrostatic attraction into full charges. So we will expand the definition into polar solvents dissolve charged solutes. A closer look at the dissociation shows that the water orients itself around the cation so that the partial negative charge on the oxygen is pointed towards the positive charge of the cation, and the partial positive charge of the hydrogen is oriented towards the negative charge of the anion, likes dissolving like. As for the basic trends in dissociation and solubility of ionic compounds, the 3 steps of the energetic process serve as a guide. Specifically, we will consider the effects on solubility of increasing size of the charge on the ion in a salt, as well as increasing physical size of the ions. To make matters a bit simpler, we will only consider aqueous solutions. That will allow us to ignore energetic step 1 when considering the trends, since separating the molecules of the solvent water will, on a first pass, be similar for the dissociation of all ionic compounds. Starting with the trend regarding increasing size of charge. What is relevant in describing this trend is the energetic cost of separating the anions and the cations. Since ionic bonding is a matter of positive charge attracted to negative charge, the size of those charges is directly proportional to the strength of the bond. Larger charges form stronger bonds, and stronger bonds take more energy to separate. The cost, step 2, of solution formation goes up. The trend concerning the solubility or dissociation of ionic compounds in water as a function of ion charge is that the larger the charges in the compound, the lower the solubility. Compounds with large charges have a saturation concentration that is lower than compounds with smaller charges. Again, that's a generalization. As for increasing size or radius of the ions in an ionic compound, the driving force in solubility is the energy release found with the solute-solvent interaction. As stated earlier, larger solute particles have more surface area to participate in intermolecular bonding with the solvent. More intermolecular bonding means more energy release. The trend concerning the solubility or dissociation of ionic compounds in water as a function of ion size is that the larger the ions in the compound, the higher the solubility. Compounds with large ions have a higher saturation concentration than compounds with smaller ions, and that is another generalization. We can take this basic understanding of dissociation of ionic compounds and review the common solubility rules. These rules are given in the student's textbook and are generally used when writing net ionic equations. While there is some variation in rules between different textbooks, they mostly follow the logic of this set of rules. Not all students will need to understand the basis of the rules, but we will cover them anyway. Rule 1. All alkali metal salts are very soluble. The alkali metals are column 1 in the periodic table. They form +1 cations. That is the smallest full positive charge. They are soluble because they have a small charge. The alkali metals will start out our table. They will be given the solubility rating of very. The only polyatomic positive ion we come across in our studies, ammonium, NH4+, form salts that are also very soluble. Ammonium is a big ion and has a small charge. Both of those features promote solubility. And then there are the halogen ions, chloride, bromide, iodide. They all form very soluble salts. The smallest halogen, fluoride, is considered a relatively insoluble ion. The periodic table shows the halogens to be in column 17 or 7b. Halogens form -1 anions. That is the smallest full negative charge. There are some exceptions to this rule. Halogens that form compounds with the cations silver 1, lead 2, or mercury 1, usually found as Hg2 with a +2 charge, will be considered as insoluble. As for the polyatomic anions, sulfate salts, SO4-2, are very soluble. All except the salts with lead 2, mercury 2, calcium, barium, and strontium. The last 3 are cations from atoms in column 2 of the periodic table. these alkaline earth metals form +2 ions. Many of the single-charged polyatomic anions form soluble salts. There are salts with nitrate, chloride, chlorate. Also, the larger acetate ion forms soluble salts. Hydroxides are a bit more complicated. Generally, they are insoluble. But here's an important tip regarding a table of solubility rules. The rules above override the rules below. Therefore, according to Rule 1, hydroxide salts of the alkali metal are also soluble. These are added as exceptions. There are a few more hydroxide salts to consider. Those alkaline earth metals that form +2 ions, well, they form moderately or slightly soluble salts with a hydroxide anion. The common -2 or -3 polyatomic anions, like carbonate, phosphate, sulfate, and chromate, are generally considered insoluble. -1 polyatomic ions are generally soluble, and larger -2 or -3 charged polyatomic ions are generally insoluble, except for salts with the alkali metal cations of Rule 1. Top rules override bottom rules. Finally, sulfites, S-2, are insoluble. Sulfites are small and have a moderate charge. This doesn't bode well with the solubility trends covered earlier. And like the rules covering hydroxides, sulfide salts with alkali metal cations and some of the alkaline earth metal cations are going to be moderately or very soluble. There are patterns in this table. It's worth considering the rules in context with each other and the energetic steps of solution formation. The last two factors on our list affecting solubility are temperature and pressure. Our coverage of these factors will be broken down by states of matter. Temperature and pressure will be covered together for solids and liquids, and covered separately for gases. Starting with solids and liquids. In all cases, the solubility of a particular solute-solvent mixture is given at a specific temperature. It is usually noted alongside the saturation concentration. Solubility in liquid of most solids and liquid solutes increases with higher temperatures. This is because at higher temperatures, the particles in the pure solvent and the pure solute have more thermal motion and therefore find it easier to overcome some of their intermolecular bonds. That is, the energetic costs of steps 1 and 2 go down with temperature. This argument can be expanded to include the interaction in step 3, but the drop in energy from steps 1 and 2 are the driving force here. As shown with this graph, the solubility of compounds like nitric acid and potassium chloride increase with increasing temperature, x-axis. More of these compounds can be dissociated at higher temperatures. They have higher saturation concentrations. However, as seen with cerium sulfate, not all compounds follow this trend. The solubility of cerium sulfate actually decreases with increasing temperature. Trends can be helpful in understanding solubility as a whole, but they should not be taken as absolutes. Because the addition of a modest amount of pressure produces very little change in the density of a solid or liquid, we can generalize that pressure has almost no effect on the solubility of liquid or solid solutes in a liquid solvent. So, for liquid and solid solutes, increased temperatures increase solubility. And for the most part, pressure does not play a big role in solubility. Gas as a solute is another thing. The solubility of a gas in a liquid solvent is a balance between gas particles dissolving in the solvent, we will call that as being captured, and dissolved gas particles escaping from the solvent. We are familiar with gas moving in and out of a solvent in the form of a carbonated beverage. Carbon dioxide is a gas found in the bubbles, which are escaping from the drink. Before we discuss the effect of temperature and pressure on the solubility of a gas, it might be helpful to expand on our understanding of what it actually means for a gas to be soluble in a liquid solvent. For that, we will use a cartoon container that has a liquid solvent with gas solute particles above and within the solution. A lid is included to eliminate evaporation. That is discussed in more detail along with vapor pressure in the colligative property lecture. Returning to the solvent, it is colored dark blue here. The molecules that make up the solvent are constantly moving around. They have thermal energy of motion and are continuously making and breaking intermolecular bonds. Now consider a gas particle above the surface of the liquid. It is freely moving about as would be expected of a gas particle. Such a particle has very high energy of motion, much more than that of the solvent molecules. For the most part, these zipping particles do not participate in intermolecular bonding. That's only slightly untrue, but we can argue no interactions because they are very short-lived. As such, when considering the energetics of solution formation, the cost of separating solute particles, step 2, is effectively zero. There are no costs here. Returning to the motion of our gas particle, at some point the gas particle will bang into the solvent. If it's going real fast, it'll probably bounce off. If it's one of the slower ones, it may actually interact with the solvent and dissolve into the solvent. The solvent has captured the gas particle. While in solution, the gas particle will move around like the solvent molecules do, because it has energy of motion, less than it did when it was free above the solution. It is continuously making and breaking intermolecular bonds with the solvent. These are competing forces, motion versus bonding. Some fraction of gas particles, however, will have enough thermal energy, motion, to overcome the intermolecular bonding with the solvent and escape from the solution back into the gas phase, where the whole process of capture and escape begins again. Solubility is the balance between capture and escape. One could think gas solubility as a measure of the amount of gas in solution captured compared to the amount of gas out of solution escaped. More soluble gases are more captured gases. With this understanding of escape and capture, we can devise some basic trends for the solubility of gas. Consider the component of capture. Anything, be it condition or substance, which reduces the capture component of this process will tend to lower the solubility. Since capture is what gets gas into solution, it makes sense that limiting this limits solubility. Conversely, anything that increases the capture aspect tends to increase the solubility. It is the reverse of the previous argument. Now, anything that decreases the capacity of the gas to escape the solution should lead to an increase in solubility. More gas molecules will remain in solution. And anything that promotes gas escaping will have the opposite effect and drive down solubility. We are now ready to see what effect temperature and pressure have on solubility of a gas in a liquid. First, to temperature, and a quick question to make a point. Consider 2 cans of soda, 2 Cokes if you will. The first one comes straight out of an ice chest full of ice water, and the second has been sitting on a table. Which one will fizz more when opened? That is the one with the lower solubility, and it proves the trend with solubility of gases. The solubility of a gas, the solute, in a liquid solvent decreases with higher temperatures. That is the exact opposite of the trend for liquid and solid solutes in a liquid solvent. The key to understanding this behavior is that increasing temperature means energy of motion, higher energy of motion. Consider the gas phase. Higher energy of motion is a faster gas particle. The faster the particle moves, the faster it will be traveling when it strikes the surface of the liquid. That means it is less likely that the solute-solvent intermolecular interactions at the surface will be strong enough to capture the gas particle. Slower particles get captured more readily than fast ones do. Capture of the gas particles goes down with increasing temperature, and therefore solubility is expected to go down. But that is only half of it. There is still the gas particle dissolved in the solvent. They too have higher energy of motion, not as much as in the gas phase, and therefore a larger portion of these gas particles will have sufficient energy to break free of the intermolecular interactions of the solution. Escape goes up. There seems to be agreement with both capture and escape. The solubility of the gas goes down with increasing temperature. That can be seen experimentally by looking at the solubilities of 4 noble gases in water with increasing temperature, x-axis. It is not always a prominent decline, but it does not go up. The effect of pressure on solubility can be argued in the same manner. We start by declaring that the pressure has a large effect on gas behavior in general, and that comes out with its solubility. Increasing pressure increases the solubility of a gas in a liquid solvent. This follows the line of reason that more pressure means more gas particles for the same given area. This comes right out of the definition of pressure of a gas. In the gas phase, with more gas particles zipping around, there will be more particles that have the right energy to be captured by the solvent. It's basic statistics. More particles means that there are more fast particles and more slow particles. There are more particles with the right energy. Capture goes up, and so does solubility, at least as far as the gas phase is concerned. Due to the high capture, there are more dissolved gas particles in the solvent. They too have thermal energy and move around. Since there are more dissolved gas particles, there are more particles with enough energy to escape. Escape will go up, which suggests that solubility should go down. There appears to be conflicting influence on the solubility due to pressure. The gas phase argues pressure increases solubility, while the dissolved phase argues that the gas should be less soluble. What gives? When the pressures increase, it means more particles in the gas phase and the dissolved phase, but there are many more particles in the gas phase. So there are more captures than escape, resulting in a net flow into the solution and a net increase in solubility. When dealing with the solubility of gases in liquids, an increase of temperature decreases solubility, and an increase in pressure increases solubility. The final component in a discussion of solubility of gases, and not all students will need to know this, is Henry's law. Again, consider gas particles moving above and within the solution. The movement of particles above the solution is the pressure of the gas. If there are other types of gases above the liquid, then the pressure due to any one particular type of gas is called its partial pressure. In 1803, William Henry noted that at constant temperature, T, there was a direct relationship between the solubility, S, of a gas and its partial pressure, P. We call it Henry's law. The specific wording is the amount of a given gas, the solute, that dissolves in a given type and volume of liquid, the solvent, is directly proportional to the partial pressure of that gas in equilibrium with that liquid. The solubility of a gas is proportional to the pressure of that gas. The proportionality constant, Kh, has to be provided. Since Kh is an experimentally determined value, a table is made available that contains gas-specific constants. Having access to the constants means that Henry's law only has two unknowns, solubility and pressure. Most Henry's law questions give a value for one of the unknowns, and the student solves for the other. That should be doable at this level of chemistry. And that completes the material for this lecture. Recapping the lecture, it has two parts, solution and solubility. For solutions, first and foremost, a solution is a homogeneous mixture of two or more pure substances. The solute is a substance dissolved in another substance. The solvent is a substance that dissolves the solute. Solubility is the ability of a substance, the solute, to dissolve in a solvent. We can also say that a soluble substance is capable of being dissolved. A saturated solution has as much solute as the solvent can dissolve. The addition of any extra solute will precipitate or drop out of solution. It will not mix homogeneously. An unsaturated solution has less than the maximum amount of solute that the solvent can dissolve. Under certain circumstances, a solution can be considered supersaturated. It will have more solute in solution than is normally allowed. It is usually unstable. The term miscible is used for liquids that can mix in all or nearly all proportions. Small alcohols are miscible in water. Immiscible is for liquids that do not mix completely or form separate layers. Think oil and water. Additional definitions that fall outside of homogeneous mixture include suspension. These are fluids that contain small particles that will eventually settle out. And then there is colloid. It is a solution with small particles of varying size, from 1 to 100 nanometers, that are evenly distributed throughout the solution. Telltale signs are a murky solution that does not filter well. We spent some time discussing the energetics of solution formation. it was broken down into 3 steps or considerations. The first 2 steps are the energetics of separating the particles before mixing, solvent and solute particles. These steps cost energy. The third is the energy releasing step. It is the energetics of solution and solvent intermolecular interactions. Now, if the sum of steps 1 and 2 is greater than the energy release of step 3, then the solute is considered insoluble in the solvent. However, if the energy release of step 3 is greater than the sum of steps 1 and 2, then the solute is considered as soluble in the solvent. Continuing on to the second part of the lecture, factors affecting solubility in a liquid. We concentrated on 3 of them. The first was the popular refrain, likes dissolve like. That is, nonpolar solvents are good at dissolving nonpolar solutes, and polar solvents are good at dissolving polar solutes. Charged particles dissolve in polar solvents, and we saw a couple trends for the solubility of ionic compounds in water. The larger the charge on an ion, the less soluble the salt tends to be. The cost of separating the solute is high. As the size of the ion increases, so does the solubility. Bigger ions can participate in more intermolecular bonds. These trends were used to sum up the solubility rules for ionic compounds in water. Solubility rules are used with net ionic equations. Another trend we looked at under the like-dissolve-like banner was the solubility of alcohols in water. Alcohols have both polar and nonpolar regions, the nonpolar region being the carbon-hydrogen bonds. The trend is that the solubility decreases with increasing amount of the nonpolar part of the molecule, the CH bonds. Temperature plays a big role in solubility. In fact, the solubility value for a solute is given at a specific temperature. We saw the trend for the solubilities of most solids and liquids increases with higher temperatures. That is in contrast to the solubility of gases. They decrease at higher temperatures. We use the perspective of gas particles being captured by or escaping from the solution as a means of explaining the temperature and pressure dependence on solubility. Factors that inhibit capture decrease solubility, while factors that promote capture increase solubility. Factors that inhibit escape of gas particles increase solubility, and factors that promote escape reduce solubility. As for pressure, it has little effect on the solubility of solids and liquid solutes. However, increasing pressure increases the solubility of a gas. The relationship that describes the proportionality between the solubility of a gas and the pressure imposed by that gas is called Henry's law. The proportionality constant Kh is found in a lookup table. And that concludes our lecture. Use your familiarity with the common liquids to help you make sense of solutions and solubility.